I've got this DC18RA battery charger from Makita. This is a battery charger that's used to charge either nickel cadmium or lithium ion batteries for the Makita brand of tools, including drills. This particular one was plugged into power. There was a kind of an extended power surge, and it immediately stopped working. So I'd like to take it apart, take a look at it, and see what's wrong with it. So here's the board, and it looks great. It's very clean. All the components are super high quality. Let's get it under the microscope. Okay, power comes in here. I just want to do a visual inspection and test a few of the components. This is the first fuse, and wow. Okay, so the very first component we checked seems like it's bad. A fuse should be able to pass current. This one isn't able to do that. Let me look through the rest of the board. And when I look through this, what I'm looking for specifically are, the various components that may be dead. These big capacitors with the tin metal on top, those are electrolytic capacitors. When they go bad, and they often do with a power surge, they're messy. They explode. Other things I'm looking for are um, other fuses or these kind of blue varistors or some of the disk capacitors. Just looking for anything that is broken, has smoke, has failed in any obvious way. And so far, everything else looks perfect. I'm very impressed. This is kind of old world technology. Just test this fuse. Yeah, and this is passing current, so it is obviously good. Um, yeah, I will just let's see. Let's take this fuse off of the board. So one thing I've got to say is that this is a very high quality piece of engineering. Every component on this board screams quality. It is made to last for decades, no problems. Um, it it uses a lot of space. Everything is a through-hole component. There's not a lot of, in fact, I don't think there are any surface-mounted devices. And this battery charger could easily be made to be a quarter of its existing size. So I'm just using some normal leaded solder to kind of lower the melting temperature so I can pull this fuse off a bit more easily. And here it is. I'm just going to use some wick and some flux to kind of clean up the holes. In preparation, I'm going to have to order this fuse in. It's probably going to take a couple of days, and I just want it to be prepared so that I can quickly get in there. And it's always a good practice to clean up the board and make it ready for the next step. Okay, here is the fuse. It is a slow fuse, a 6.3 amp, 250-volt fuse. Kind of wonder what's inside of it. I'm just going to order it. It should get in a couple of days. In the meantime, just a little about these fuses. It's a slow fuse, meaning that it can withstand an occasional power surge before it will blow, and in this case, it must have before it went out. It's supposed to be filled with some sort of ceramic material or something that'll kind of allow it to withstand a little bit of a power surge before it finally fails. Okay, that looks like it's full of something like salt, but probably isn't. I'm going to clean that up and order the part. So it turns out that material was not salt, and it was in fact sand. So no problem to clean it up. These fuses are made apparently by putting inside the ceramic casing a coil of wire, and in that wire there's a small blob of solder that will break more easily, and then packed with sand. The combination of those things allows it to take a few small power surges before it explodes. And here is the board. I'm just going to place it on there. Looks like it is the right size and the right part. This fuse, by the way, costs less than $1, so it's well worth it to repair your own. I just need to put some gloves on and we'll solder that on the board and then we can test it.